Okay, so this should be pretty quick today. What we're going to talk about now is a significance test for a difference of means. So we just did confidence intervals, so now we're going to do significance tests. So again, our conditions don't change. If one or both of the populations is less than 30, we have to graph and check for no outliers or strong skewness. So again, nothing there's changed. We know all of this stuff here. Just to highlight again, experiment, we don't check the 10% condition. Okay, so two sample t-test for population means. So remember, with a t-test, so when we have a test, what we're doing is we have a null hypothesis, and then we're going to have some sort of alternative hypothesis. Okay, now we can write this null hypothesis as one mean equals the second mean, or we can say mean 1 minus mean 2 is going to equal 0. So either one of these would be okay for our null hypothesis. When we have our alternative hypothesis, we're going to say either mean 1 is greater than mean 2, or it is going to be less than mean 2, or it's just not going to be equal to mean 2. Okay, so this is what we have when we have our alternative hypothesis. So everything that we did before is going to stay the same. So everything with error, everything with our alternative hypothesis, all of this, nothing's changed. What does change, however, is we have this t-test now because we're dealing with means. So t-test and means are the two things that go together. So let's look at our formula. So our formula now is t star. So let's go back to our cheat sheet. And what we have is we have this standardized test statistic. And this standardized test statistic, we've always looked at this as just our z value. And our z star value is the statistic minus the parameter over our standard deviation. Okay, so if we looked at that, we would say that our z star value would be x bar minus mu over our standard deviation. So this is what we've always used in the past. Now with t-star, it's going to be a little different. It is nowhere on your formula sheet. So you have to really understand this part of the formula or understand what this talks about when it says standardized test statistic. So now we're not z anymore, we're t. So what this looks like is we have x bar 1 minus x bar 2. This is going to be my this x bar. Okay, now what we're subtracting here is we're subtracting this mean, and this mean here is our population. So we're saying that this is our given, and our given is our parameter value. So if this is my parameter value, what I'm saying is that's the same as saying we subtract 0. So this part actually we don't even need to write down, but just to show you where this comes from here is we say that this value of mu is going to be equal to 0. And this falls underneath our standard deviation of our first sample squared over our sample size, and then our second sample squared over that sample size. So this is the formula that I'm going to use when I calculate my t-star value. So again, when we're looking at a t-test, we want to find the p-value by calculating the probability of getting a t-statistic as large or larger in the direction specified by our alternative hypothesis. So we're going to use this t-distribution with degrees of freedom. This hasn't changed by approximating the smaller, so either n1 minus 1 or n2 minus 1, or the degrees of freedom given by technology. And what we know is that we saw this when we did a confidence interval, that this degrees of freedom is going to be given on our calc. So you're going to use one of the two here. You just have to list which one you're going to use. And then, of course, we have to define our alternative hypothesis like I showed up here. All right, so let's jump into our example. So, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed relationship between calcium intake and blood pressure, and the relationship was strongest for black men. Because observational studies do not allow for us to draw a cause and effect conclusion, so observational studies do not allow for us to draw a cause and effect conclusion, a randomized experiment was designed. The subjects were 21 healthy black men who volunteered to take part in a double-blind experiment. They were randomly assigned to 2 groups. 10 of the men received the calcium supplement. So 10 received the calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The response variable is the decrease in the systolic, which is the top blood pressure number for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative number. Okay, so before we look at the data, which is here on the back, before we look at this data, let's figure out why we're doing a 2-sample t-test. So what we have here is we have 2 samples. So they either received the calcium or they received the placebo. So again, this is not a matched pairs design. If it was matched pairs, they would be getting both of these, right? The other thing here is it says an increase appears as a negative number. So we want the calcium number to be higher so that we have a positive value. All right. So if let's go ahead and plug this data in. Do the data provide convincing evidence that the calcium supplement reduces blood pressure more than the placebo? Carry out an appropriate test to support your answer and interpret the p-value in context. Okay, so step 1 is I've got to put this data in my calculator. So let me go ahead and do that. So I'm going to go ahead and pause the video. You do the same and go ahead and put your data into L1 and L2. Okay, so here's my data. So let me go ahead. I've got this right here. I'm just going to set this aside for a minute. Let's go ahead and do everything that we need here. So here's my communicate statement. So my communicate, my first thing that I'm going to have here is that I'm going to label this mu sub c, and this is going to be the mean difference, not difference, decrease. It's a decrease in blood pressure for the calcium group. And then I'm going to do this one as U sub p, and this is going to be the mean decrease in blood pressure for the placebo group. All right, so now since this is a significance test, I have to do my null hypothesis, and my null hypothesis is going to say that the calcium group is going to equal the placebo group. So this is what we want to disprove that these are equal. So my alternative hypothesis is going to be that the calcium group is higher than the placebo group. If it's higher, that means we're going to have a positive result. If we want a positive result, then we know that it was effective. Okay, now it doesn't say anything in here about a significance level. So because there's nothing in here about a significance level, I'm going to say that my significance level that I'm going to test this at is going to be a 5%. So this is a default if we don't know. Just like if we don't know a proportion, we use 0.5. This is going to be the same thing. If we don't know a significance level, we're going to use 0.05. Okay, so let me, I guess I can go in here and run this data right now. So if I go into stat, my 1 bars data, let me do my list 1 first. All right, so here's what I know. I know that my X bar of my calcium group is going to be 5, and my standard deviation of this group is going to be 8.743. And I also know that in this group I have 10 subjects. All right, so let me run this again. And this time I want to run list 2. And this is going to be X bar of placebo group is negative 0.273. Standard deviation of the placebo group is 5.9. And my N of the placebo group is going to be 11. Okay, so here's what I know. And so now I'm going to go in and look at my conditions. So first thing that I have here is that this is random assignment. And don't put SRS because it's not. So if we go back and look over here, it tells us Even though they volunteered, so the men who volunteered to take part, they were randomly assigned into two groups. Okay, so we do have random assignment, so that checks that box. Independence, I'm going to say not necessary because it's an experiment. And then I want to check for its normal here. And what I don't know is that I don't know anything about whether these distributions are independently approximately normal. What I do know is that 10 is less than or equal to 30, and 11 is less than or equal to 30. So I have to check the graphs. So if I go back over here, my stat plot's on. I'm going to go ahead and do list one first, just to stay consistent. Zoom 9, and that's my graph right there. And so here I'm going to have my frequency, and my list one is my calcium group. So if I look at this, I have something that looks like this. I need to have some numbers on here. So if I hit trace, so this is going to be from -5 to 4, and this is quantity 5. Oh, sorry, that's 4, quantity of 4. And then this goes to 6.5, 12.5, 18, and 23. Okay, and again, I'm going through this really quick. I mean, this is an awful histogram. These are not all the same size, but I'm really hopeful that you don't have to draw one of these, that the graphs are given. So I'm going to do it again. This time, my stat plot, I want to look at list 2. Let me graph that. Okay, so this looks like this is a little bit more funky here. So what I'm going to do on this one is I'm going to go in and change my window. So this would be my placebo group. And if I look at my data up here for the placebo group, it looks like I go from -11 to 12. So on my window, I'm going to say -11, and I'm going to make my max 12, and I'm going to make, actually let me do this way, -12 to 12, and I'm going to make my scale at 2. And let's see what that looks like. That doesn't look any better. Let me change this and make my scale this time 5. Okay, there we go. I'm going to use this one. So if I hit trace, I have this first value, which is -12 to -7, and this is 1. So this is my quantity of 1. And then I have this guy here, and then this guy here, and then here, and then back down to 1. All right, so if I get my values real quick, -2, 3, 8, and 13. Okay, so you see how important it is to look at your scale. So what I'm going to say here is that neither distribution is significantly skewed or has obvious outliers. Therefore, use approximately normal, or assume approximately normal. All right, let's get into the calculations now. So we go down here to calculations. So what am I using? I'm using a 2-sample t-test for means. All right, so here's my t-star value that I'm going to calculate. I have my calcium minus my placebo, minus 0, so I'm going to leave that off, over the standard deviation of the calcium squared over n calcium plus the standard deviation of placebo squared over n placebo. So if I plug these values in, and all these values come from up above here, I would have 5 plus 0.273, because it's minus a negative, over the square root of 8.743 squared over 10 plus 5.9 squared over 11. All right, so I plug this bad boy in to my calculator here, and I have 5.273 in the numerator. In the denominator, I have plus all right, so this gives me a T star value of 1.604. All right, so now what I have is because my alternative hypothesis says that this is going to be greater, I want to have the values that are higher than this. So if I look at my curve here, I've got this value of 1.604, and I want this data. That's going to give me my p-value data. So this is what I want. So when I plug this in, and I go to distribution is what I want. And I'm going to look at TCDF. I look at TCDF because this is, I'm running a T test on this. My lower bound is 1.604. My upper bound is here. All right, so let's talk about degrees of freedom. So I need to list my degrees of freedom. So degrees of freedom are going to be the smaller of the two. So here my degrees of freedom would be 9, and here my degrees of freedom would be 10. So I'm going to use this degrees of freedom of 9 because that's the smaller of the two numbers. So I use 9, and this gives me a p-value of 0.0716. That's my p-value. All right, so what does that, I ran out of room again. Let me grab another piece of paper. Sorry, y'all. So let's talk about our conclusion. Let's work on our conclusion here. So last step, my conclusion. So because our p-value, which is 0.0716, is greater than alpha equals 0.05. So here's what I have. 0.0716 is greater than 0.05. Because of this, we fail to reject the null. All right, so now we can say we do not have convincing evidence that calcium supplements reduce blood pressure more than a placebo. All right, so let's go back up here and make sure we answered the question. So carry out the appropriate tests to support your answer and then interpret the p-value. So there's two parts to this. So don't just assume that we can write this conclusion and then we're done. So this asks for two things. So carry out the support your answer and then interpret the p-value you got in the context of this experiment. All right, so what we did is we said that we failed to reject the null, but if I talk specifically about my p-value, what I have here is that basically if calcium has no effect on the blood pressure, then the probability, so let me write this. If calcium has no effect on blood pressure, the probability we get a difference of 5.273, that's this number right here, right? That's the difference in my means. The probability we get a difference of 5.273 or larger is 0.0716. So let's talk about this specifically. So we get this p-value here of 0.0716. So this is my probability. I could have also written this as 7.16%, right? And the reason we get this, the probability we get a difference of 5.273. So this is the difference. So if I look at calcium minus placebo, we said that because the placebo was a negative number, we're going to add these up. That's where this comes from. So the probability we get a difference of 5.273 or larger because this is the value that I have here. It's getting bigger than my t-value, is 7.16. All right. And so make sure when you're reading your problem statement, you go back and you have all of the context was included in there.